Hello everybody and welcome to the second video in our classification chapter where we are talking slowly on logistic regression. And in last video we defined logistic regression as a classification problem where we have only two classes to predict. That means our y either equals 1 or 0. And that's exactly what logistic regression is. And we also knew the fact that logistic regression doesn't have anything to do with regression. So yeah, let's see what we are going to study in this video. And so in this video we're gonna see more information about logistic regression, and then we're gonna see something very important called the decision boundary, and then some different shapes of decision boundary. So we said last video that actually in logistic regression what we are trying to do is to calculate the probability of y equals 1 given x, y, and b. And that's by calculating h of x. And we said that the sigmoid function actually give us exactly like output values exactly between 0 and 1, where at the point where x equals 0, exactly at 0.5. So yeah, that's our new h of x. We defined the h of x. We said that if h of x is bigger or equals 0.5, then we predict that our y equals 1. Else, that means if h of x is less than 0.5, we predict that our y equals 0. And we had the example of the tumor size, like benign or not. So we noticed that, like very important notice, when x is more or equals 0, that means here and more, the sigmoid of x is more or equals 0.5 here, exactly this point. And at the opposite side, when x is less or equals 0, the sigmoid of x is less or equals 0.5. So from here. So our x in this case is wx plus b, as we said before, because we are trying to define like some hypothesis function with parameters that we can learn. And in this case, these parameters are the w and the b, the bias. So let's talk about decision boundary, putting in mind what we just learned here, because it has to do something with the decision boundary. So you can imagine the decision boundary as the line that splits two classes. For example, we have these two classes. We have here like the breast cancer example. We have the age, the tumor size, that means we have two x's. Then we want to, like, in this area, you can notice that these are the malignant tumors, and this is the benign tumors, and we want to split them on two. So let's put h of x equals the sigmoid of x transpose w. You remember our vector representation, x transpose w. That means the matrix of x transpose multiplied by the matrix w plus the vector b. B is, in this case, is like almost, I've never noted seen a B as a matrix. It's always a vector. I'm not sure if it's even like possible to be a matrix. So anyway, in other words, the h of x equals sigmoid, the tumor size, multiplied by the w1, this is 1, w1, So we have tumor size, which is x1 multiplied by w1, and the age multiplied by w2 here, plus the bias. So assuming that, let's put like, just assume that w1 equals 1, w2 equals 1, and and the bias equals -4. That means y equals 1 if tumor size plus age, because the w1 is 1 and the w2 is 1 also. So tumor size plus age -4 is more or equal 0. In other words, tumor size plus age is more or equals 4 here. So yeah, is more or equals 4. And predicts 0 if the opposites. So we predict y equals 1 if tumor size plus age is more or equals 4, and the opposite means 0 if tumor size plus age is less than 4. By this given equations, we can say that, you can see here like 1, 2, 3, 4. So we can say that we learned this line here given our h of x. So we learned, so this line actually splits the data, like the benign tumors and the malignant tumors, using the tumor size and the age and applying our h of x. And this is what we wanted to get to from the beginning. This line, the line that splits the data, is called the decision boundary. Why? As you may like guess, because it's kind of obvious, because it makes the decision, like this line is the decision, is where we make the decision, is it like malignant or not. If we are up on this line, we say yes, it's malignant. If we have, like, for example, new tumor and it's here, like its location is here, the age is almost like here, and the tumor size is here, we predict that this tumor is malignant. And if we have like a new tumor and it comes here, we predict it's benign tumor. So we say that this line is our decision boundary. So as you might already know, that the decision boundary is not just a line. The decision boundary can come in different shapes, in other than just straight line. For example, here, if we have like this x2, x1 and x2, like two features, and this is the how like our data is split, you can say that the decision boundary is here. So every single time we're gonna have like some data with two classes, we don't know what's like this how the data is gonna be, we're gonna try to learn this decision boundary. So this is the new goal. The goal of logistic regression, please listen to this carefully. The goal of logistic regression is to learn the decision boundary by manipulating the parameters. So this is our goal here, to learn this decision boundary that splits the data. For example, in our cancer example, tumors, malignant or not malignant, and so on. So y equals 1 if x plus x2, x1 plus x2 is more or equals 1. So this is 1. So x1 plus x2 more or equals 1. So yeah, I think there is actually a better like function to draw this decision boundary, which is like a circle. You can see it's a circle, so you can see x square plus x1 square plus x2 square equals 1, and that gives us this circle. And this is how we this is what's like our decision boundary. I already learned the decision boundary without any gradient descent, without anything, just by looking to the figure. You can sometimes you can learn the decision boundary, but sometimes it's really like hard, because the decision boundary can come like line like this, like I'm moving the mouse now, so you never know. So in next videos, we will start to learn how to learn the parameters to draw the decision boundary automatically. As you might already remember, our first videos of linear regression, we used gradient descent. Also with the logistic regression, we're gonna use gradient descent, but we're gonna have some different things. I'm gonna let it for next videos to see. And so this was our video this time, and thank you very much. If you didn't understand, just try to watch the video again, and like maybe even search out there in the internet for some concepts if you don't understand well. And I hope you understand everything. Thank you very much, and see you next video.